Today we are talking about water chemistry. This is the last kind of component as we talk about oceanography. We've talked about geography. We've talked about physics with thermohaline cycling and how water moves. The last thing we're going to talk about is the chemical composition of the water itself. This is a review because I know you've just taken chemistry, and we talked about in biology, we talked about water chemistry in general. So we're just going to add in a few more components about why ocean water is unique and some issues that come into play when things get thrown off. So to warm up, I want you to think about what differences are there between ocean water and either lake water or tap water. So these would be three separate categories here. So obviously tap water, it's going to be the most pure probably of the three. Pure, I guess, is up to opinion. It's going to be cleaner in terms of bacteria and waste, but it is going to have additives in terms of chlorine. It could have like bits of metal, like molecular level pieces of metal that have leached from pipes. So there's going to be different things in there, but we can drink it. Lake water is going to be more natural, hopefully have less chemicals as long as it's not polluted, but it is going to have some microorganisms living in there. So if you've ever looked at lake water under a microscope or seen experiments where you could scoop up a cup of lake water and like keep it in a jar and it becomes a little ecosystem because it has very small like microalgae and then microorganisms that are living in there. The big difference, I guess, chemically would be that it is not going to have any salt in it. It's still fresh water, unlike our last one, ocean water, which obviously the big difference is that it has salt in it. The ocean is salt water. So it's going to be similar to lake water, though. Lake water is kind of like our middleman. It doesn't have salt, but it does have other naturally occurring either biomolecules or inorganic, but like natural minerals in there. Tap water is going to be fresh water, but it's not going to have any, it shouldn't have any microorganisms or remnants of them in it. So for ocean chemistry, we are going to just look at the chemical composition, like I said, of our ocean water. This is going to be very important as we move forward and look at the living things in there because a lot are affected by salinity. There's a reason that freshwater fish can't live in salt water and vice versa. There's reasons that different animals live at different places of the ocean based on its chemistry. So just a rundown of the vocabulary we'll come into today. A lot of this has to do with just how water acts in general, and then one last one talking about the ocean. So hydrogen bonds, as a reminder, are a weak attraction between polar molecules. So hydrogen is very weakly electronegative. It doesn't hold on to its electrons very well. So things that have hydrogen in it tend to form like slightly positive regions on those molecules, which makes them polar, which means that they're attracted to the negatively charged areas of other atoms. Ionic bonds are bonds between negative and positive ions. The electrons are not shared, they are given. And this is going to be very important for salinity because salts are made through ionic bonding. The heat capacity of a substance is the amount of heat that it can actually absorb, the amount of energy it takes in before it actually increases its own temperature. So it seems a little counterintuitive that if you give heat to something, it should increase its own temperature, it should heat up, but certain substances heat up quicker than others. A solvent is a liquid that can dissolve something, and then the solute is the material that you dissolve. So for today, we're mostly going to talk about salt being a solute and water being a solvent. And the last one is the water column. So this is an imaginary vertical column of water that extends from the surface of the ocean to the bottom. So it's just a way that we look at the differences in water's properties near the surface of the ocean as we get further down. So when we talk about the water column, we just mean if you were to take a look vertically at water in the ocean. Okay, so to begin with, as a reminder, we talk about this all the time in science. Water is a unique liquid, and it's something that we don't think about very often because it's the basis of life on Earth. So we just kind of accept the way that water acts, but it acts very differently than any other liquid. And that's due to three separate things that are a little bit related, all about those hydrogen bonds. But the first one is that it is polar. It has polarity. Its molecules are not evenly charged, so that's going to affect how it interacts with things. It also has a high heat capacity, so it can absorb a lot of heat before it raises its own temperature. And then the third is that it is the universal solvent, is what it's called. So we are going to go through each of these individually. As a reminder, you've probably all seen this before, a water molecule is made of two hydrogen atoms, shown here with their partially positive charge, and one oxygen atom. And because of the electronegativity, the orbiting of the electrons, here, this is the shape that it takes on. It looks like a Mickey Mouse head. So we end up with unpaired electrons, or sorry, unjoined electrons, like electron pairs at the top, and then electrons that have paired with the hydrogens down at the bottom. So because of this, because it doesn't, there's this bend here, there isn't a straight line, it doesn't show up just as a straight molecule with hydrogen, oxygen, hydrogen, it leads to these regions where the red is showing a partial negative and the blue is showing a partial positive. So the difference in electronegativity of the atoms creates those charges at each side. And so they act almost like poles of a magnet. And this allows for hydrogen bonds to form between our water molecules. So our partially positive hydrogen atoms attract to the partially negative hydrogen atoms, or oxygen atoms, sorry, of the other water molecules. So in this drawing, you can just see where these bonds would form. And this is going to make a big difference on how water behaves. So one of the differences it's going to make is the density of water at different states or phases of matter. So as it changes from a gas to a liquid to a solid as it cools down. So most materials follow this pattern where we have our density of matter that as a gas is less dense, or it's the least dense, and then as a liquid those molecules come back together, and then as a solid they are fully packed in as densely as possible. So the reason for that is because of the energy that they have. This is a still image, but really these molecules would be bouncing around, and they have too much energy to stay close together. They're just pinging around as a gas. As a liquid, those bonds are not formed very well, the attraction between our molecules. So they just kind of slide past each other, but they're pretty densely there. This is why liquids don't have a solid shape or a fixed shape. And then solids, these are not permanent, but they are fixed bonds here. So they're not going to move against each other. However, this is not how water acts. So because of those hydrogen bonds, the fact that these molecules have to line up so that a negatively charged oxygen region is closest to a positively charged hydrogen region. Just like when you have two magnets, if you try and bring the north side of two magnets together, they will repel. The same thing is going to happen with our water molecules. So you have to line them up so that it's negative, positive, negative, positive. And because of this bend, the angle between our positive sides here with the hydrogens, they end up making these very regular patterns that they form these hexagon shapes as they form these bonds. So these bonds only really show up when they are in a solid form. So what happens there is you can see there's a lot of spacing between the molecules in ice, whereas once it's melted into water, they can kind of bump past each other and come closer together. So that means that as water cools down, as we have liquid water cool down, it does get more dense, but as it forms that solid structure, it starts to make these formations that pull the molecules back apart and become less dense. So ice is one of the only solids where it is less dense as a solid than it is as a liquid state. So we'll see what that leads us to. This is an aside here. This is also why snowflakes have such intricate 6-pointed structures. They always have 6 points because the structure of ice is such that it always has hexagons in it. So our point here is that ice is going to float on the ocean surface, but cold water is going to sink. So we already talked about this in terms of currents, that is what drives our thermohaline cycling, is that cold water sinks. This is also very important, just that icebergs are going to float. Sea ice is going to stay on the surface of our oceans. And in terms of the buoyancy, if you've taken physics before, buoyancy is like the ability of an object to float. So an object will displace the amount of liquid that's equal to its own mass. So we can see here that this iceberg, the mass that it has of the entire iceberg is equal to the mass of water just at this underwater part. So it's not super buoyant. It's not incredibly less dense. It's not like putting like a beach ball, something with a gas on top of the water, but it is less buoyant, or I apologize, less dense, more buoyant. So part of this is something that I haven't heard in a while, to be fair, but something that I was told in high school is that climate change is not going to lead to oceans rising. It's a myth because of buoyancy, and this iceberg, when it melts, is just going to fill in the water at that spot. And that part is true. Icebergs are not going to be the cause of a change in sea level rising. So I want you to think, this is going to be one of the questions that you have to answer for this presentation, is why is climate change causing rising seas? This is a thing that's going to happen. This picture here should help you out with the question. So we'll pause for a minute here. Okay, so the point is, if somebody argues this to you, is that the icebergs are not the only place that ice exists on Earth. There's a huge amount of ice on land that is melting into the oceans and just streaming in there. So that comes from glaciers, which you can see here. These are glaciers, and we will talk about those later. Ice sheets like the continent of Antarctica, which is in fact resting on land, but has thick layers of ice, and those are starting to break off and add new water, new liquid into the ocean. So this is where the rising seas come from, is land ice that also melts. So if somebody tells you it's icebergs are all a myth and it's all made up, come back with them with glaciers. The second part that we're going to talk about is the universal solvent nature of water. So water is called the universal solvent because it dissolves more things than any other natural substance on Earth. It can't dissolve everything, obviously. A lot of things do not fall apart in water, but way more things do than we think of for other liquids. So anything that is a polar molecule, anything else that has slight charges on either side, and anything that is an ion will readily dissolve. And salts dissolve very, very well because of their ionic bond. So that's what we're going to look at here. So what a salt is, we think of salt as sodium chloride, as table salt, but really any metal and nonmetal that bond together through an ionic bond are considered a salt. So you can also find things like potassium chloride, calcium chloride. These are all salts. They're just not table salts. But any salt is going to follow this pattern, that because they are made of ionic bonds, they're just associated because their electrons cause attraction between them. They're not actually bonded together. When they are in water, these polar molecules are going to interrupt that bonding and dissolve the salt. So you can see here we have our water molecules, and as we look at, if you look closely at this center image or the one on the right, when you're around the larger molecule, this is going to be the negative ion. You can see that all of these water molecules are pointed with the hydrogen side in, the white side in. And if we look at the blue, the smaller ones, these are going to be the positive ions because they are attracted to the negative side, the oxygen side of our water molecule. So this is why salt dissolves when you put it in water. So seawater, it is salt water, but it's a little more complicated than that. Many materials are dissolved in seawater. So they can come from land, things that drain off into the ocean, or from the shore that then dissolve into the ocean, like minerals, organic matter from the soil, or organic molecules from the soil. Precipitation, so anything that is in our rainwater is going to then join the seawater. So for better or worse, those could be naturally occurring minerals, or it could be pollution that gets stuck in our water cycle. And then from the Earth's interior, so when we looked at our constructive plate boundaries, when we looked at geography and plate tectonics, where that magma comes up, the lava as it gets to the surface, comes up from the mantle and forms new Earth. It also releases gases and small pieces of those minerals into the water that get dissolved. And these are going to be really important for life in the ocean. The most common solutes that you'll see are going to be from dissolved salts, though. So sodium chloride, but also some other salts that we'll look at. So we can see the seawater here, a little bit cloudy. That is normal. So the salts that come in seawater, they are separated out because these are the ions that have dissociated out of the salts that are in seawater. So the biggest contributor is chloride. Chloride will form a bond with several of these substances here. It's a negative ion. So any of these things, sodium should have a plus side there. Chloride forms a salt with as sodium chloride, as magnesium chloride, as potassium chloride, and as calcium chloride. It's half of all the ions in the ocean are chloride. Sodium chloride, so this is why if you get seawater in your mouth, it tastes like table salt, because that sodium chloride is about 30% of the salinity. There are also sulfates, magnesium, potassium, calcium, bicarbonate, which is we call baking soda, and then bromide. So these are all things, if you look at these, they're all things that should be in like a multivitamin, They're all things that living things generally need, and that is not a coincidence. This is why it's able to sustain life, is that the salts that and minerals that we need for our body are in there. So as we go through, we have a salinity. Sorry, I'll pull that out. Of the total dissolved solids in the ocean are 3,500 parts per million is what ppm stands for. So this means out of a million molecules in the ocean, 3,500 of them are going to be salts. It's also written like just a salinity of 35, and that would be 35 parts per thousand, I believe. I think I have it on the next page. But you'll see as you look at different creatures, sorry for that, different regions will describe their salinity, and it'll usually either be in parts per million or in this whole number here, like the smaller number of 35. Okay, so the salinity of seawater. Well, as I've said several times now, I got ahead of myself, sea life requires specific salinities. So each organism will have a different, based on where it evolved, will have a different requirement for the salinity of its seawater. Some are adapted to lower salinities, what we can call brackish water sometimes, which is kind of midway between saltwater, ocean water, and freshwater. Some can live in really high salinities. It really just depends on the organism. The reason that they have to have a specific salinity, like we don't have these types of requirements. We can go like sit in freshwater, we can sit in saltwater, we can sit in like high humidities and low humidity areas because our bodies regulate our salt for us. So through our kidneys, we can keep our salt levels regulated, and when those get off, that's when you like crave salty food. We are adapted to this. A lot of sea creatures are not adapted to that, so they just absorb the salt water straight through their skin into their bodies or through their cell membranes for our non-skinned animals. So we'll see that as we look at different creatures. The average salinity is 35 parts per thousand, is what that 35 is from. So it looks like a percentage sign with an extra zero because this would be per 100, and since 1,000 is 10 times more, they put this extra zero there. So this means parts per thousand. You can also say PPT. It's very uniform in the ocean. Like the water has been mixed. It doesn't get changed that much. It's kind of like when we talked about temperature. The temperature of the open oceans doesn't vary as much as it does closer to shore, where it's going to be impacted by not impacted by the temperature on land, sorry, because there's less water there. It's shallower and kind of closer to the shore. It would heat up or cool down faster. Open ocean is going to be our average place. The places where it's going to vary a lot are going to be closed off regions where the salinity can get very high, up to 40 parts per thousand, which doesn't seem that high, but can get dangerously high for animals. So these are places like the Dead Sea, and the reason for that is, as we talked about with the thermohaline cycling, is that evaporation only affects the water molecules. It does not bring the salts with it. So the salinity in closed off regions can get higher. And then along coasts, it can get as low as 7 parts per thousand. So that's obviously much more extreme. The reason for that, I don't have on there. So the reason for that, you can probably guess, but it's because there's going to be a lot of freshwater runoff or input from rivers. So along coastlines, obviously, all the fresh water that comes from our rivers and streams is going to enter ecosystems. So at the deltas of rivers, those are the openings of rivers, we will see like a very gradual change from freshwater to saltwater, and that's where we get these 7%. There's also going to be more runoff just from like rainwater, precipitation, and other runoff from the land, which is all going to be freshwater. So as you get further away from shore, we're going to move over to this 35%, but we can have regions. We have one really close to school at Ballona that we consider a brackish or a like in-between salinity. So we're going to have unique organisms there that are adapted to brackish water. Okay, the other things that are dissolved in there, the reason that ocean water is not just salt water, it's pretty unique and difficult to replicate, we'll talk about this a lot this year, is that there are going to be nutrients in there and other gases. So nutrients, I talked about last week with the thermohaline cycling, is one of the reasons that the ocean currents, the upwelling of water from deeper regions, is really important, is because it brings nutrients from like dead organic matter, rotted away organisms are going to provide nutrients like nitrogen, phosphorus, and iron from their bodies that can then be brought into the bodies of new living organisms. So we need those nutrients. And then gases that are going to dissolve into there. So water is very good at dissolving some gases. So oxygen gets dissolved in there. Carbon dioxide, obviously, from animals giving off carbon dioxide. And then nitrogen from the air is also going to be in there, which also acts as a nutrient. But there are different forms of nitrogen, which we will get into when we talk about pollution. This is an important part here, is that the oxygen, this is kind of a misconception sometimes, the oxygen that fish and other ocean creatures, ocean animals breathe or extract from the water through their gills is not the oxygen that's in the water molecule. They do not break down water molecules. There are other oxygen molecules that are floating within the water that they can then filter out. Okay, last thing we're going to talk about is, this is where we talk about the water column, is the thermocline. So as you get deeper into the ocean, we are going to see the temperature drop and salinity increase. This has to do with the density. This gets really intertwined with the physics of water that we've already talked about. So this is what drives thermohaline cycling as well. So thermo obviously means temperature, and cline is like an incline or decline, like a change, a slope that we see. So in the first 1,000 feet, we will see a very drastic drop in temperature and in salinity of our water from our surface, where it's about 22 degrees Celsius, and then goes down to about 4 degrees Celsius in 1,000 feet. In the next, however deep of the ocean you get to the ocean floor, it can only go from 4 degrees down to 0 degrees, which is the freezing point of water. So it is very, very, very cold later in, deeper in the ocean. Sorry, let me go back. This is also going to affect the salinity. The salinity increases as we go down. So as we're looking at the chemistry, we will see very dense salty water as we go down. And the way that we know that is by taking water samples. So this is just something to know of how we can test things as we are in places we can't go to. How a scientist will take water samples is that they'll have this contraption that sinks, it's like anchored, weighted down, that they will lower, and each of these bottles is closed at the moment, It has thermometers inside, and they will drop this whole contraption down, and then at certain depths, it will trigger each of these bottles to open, let in water, take the temperature, and then shut again to collect an actual sample of the water. And they'll do that for several different depths, and so then they can accurately test. When they pull this back up, they can see what reading the thermometer got while it was open, and then actually chemically test the water that was there. Okay, and this I will pull up. When I talked about different types of nitrogen in the ocean and how that's going to affect our water, we will discuss this later, so I'll pull this video up for you to look at as well. So that's it. That's a lot about chemistry, but it's going to just be base knowledge that we are going to come back to as we talk about different environmental issues, different ecology issues, and just different organisms and why they live where they do. So hopefully this was a good refresher on our chemistry principles.